Good morning again. So you would have received your graphs, and you would have seen that I would have marked and given feedback where applicable, right? So where some persons, would have lost marks, I would have indicated why you would have lost those marks, right? Maybe because of not including everything that is required for the graph, or some errors, right? I would have indicated on your graph so that going forward, you can be aware of the corrections so you don't make the same mistakes again. All right, so we're going to continue with our discussion, Williams. Yes, so we're going to continue our discussion this morning. So we would have spent some time last time looking at vectors, right? And prior to that, we introduced the topic of forces, right? We introduced the topic of forces, and we can remember us saying that a force is a what? Do you remember? What is a force? It's a push or a pull, right? And we would have stated also that, when a force acts on an object, it can cause some change, right? Whether a change in its speed, its shape, its size, or its direction, right? So we see that effectively that a force will cause some effect when it acts on an object. Now, we should remember, based on our discussion related to vectors, that force is an example of a what type of quantity? Scalar or vector? Force, is it a scalar or a vector quantity? Vector quantity. Why a vector quantity? Because it has magnitude as well as direction. Because you can talk about a force acting in a particular direction of a certain magnitude. Okay, so I can push here with a force of, let's say, 10 newtons in that direction, and I can push in this direction with that same 10 Newton force. So we can talk about the magnitude as well as its direction. So therefore it is a vector quantity, right? And we should also be aware from before that force is measured in newtons, okay? So what we're going to do now today is we're going to actually continue discussing forces, and we're going to establish a formula, right, that we can use to actually relate the force on an object. All right, so let's go into this right now. So we're talking about forces. All right? Forces. Now, we would have went in and discussed that a force causes a change in an object, whether a change in its speed, its direction, its shape, right? Now, what we're going to do now is we're going to actually talk about when we have more than one forces acting, right? So we're going to start by relating the fact that, okay, force is a vector quantity, right? And remember we said that, okay, when we have multiple vectors acting, we can find the combined effect. And we call that what? What's the name we give to that single vector we get, which represents the overall effect? What's that? The resultant, right? So we can talk about the resultant. And in this case, now we're going to talk about the resultant force or the net force. But before we get to that, we're going to preface this by saying that when multiple forces act on an object, we can determine the net effect of those forces, right, by considering what we call now vector addition. Right? So, due to the fact that we know that force is a vector, if we have more than one forces acting, we have to determine their resultant by considering vector addition. And again, remember, the resultant is just the overall effect, okay, of those forces acting. Right? And again, we have to use vector addition because force is a vector quantity. Yes? Force is a vector quantity. Why not taking down the notes? All right? So we can use vector addition. Now, the net effect or the net force, well, let me not say that net. Let's say the net effect of multiple forces acting on a system is called the resultant force or the net force. All right? So we can call the net effect of multiple forces on a system the resultant force or the net force. Right? The resultant force or the net force. Okay? All right? Two effect? Yeah, thanks. All right? Net effect of multiple forces acting on a system is called the resultant force or the net force. Right? And you will also see in some textbooks they might say, the unbalanced force. Right? But for our purposes, we're going to use the terms resultant force or the net force. And we're going to sketch a little diagram to see if we can actually illustrate this right here. All right, I'm going to sketch two diagrams here. So let's say we have a box right here, kind of similar to my example with the toy car. Let's say we have a box, and let's say that we have two forces acting on this box. Let's say this is FA, and let's say we have this one right here. And if we call this one FA, we can call this one what? FB, right? Right, FB. So these are our two forces. We have FA and we have FB acting on this system right here. And we can talk about the resultant force, right? Or the net force acting on this box. Because again, we have force, which is a vector quantity, and we have multiple forces acting on this box right here. Okay? Now, we'll remember that when we talk about vectors, which force is a type of vector quantity. When we have vectors, if we have, let's say, two vectors acting in the same direction, right, we can determine their resultant by doing what? Or we can determine the magnitude of the resultant by doing what? Just adding, right? So therefore, what we're going to see now is that in this case, the resultant force or the net force due to these two forces acting will just be the sum. So we see now that we can write that F net is going to be equal to what? F net is going to be equal to what? FA plus FB, right? FA plus FB. All right? So this would be our net force or the resultant force due to these two forces acting on this object right here. Now, similarly, or on the other hand, if we look at another example, let's say, same box like this. But in this case, let's say we have, we still have FA going this way. So this is FA. But we have FB going like this. Right? In this case, we see that the forces are acting in opposite direction. Right? So once we have vectors in opposite direction, we always do what? Subtract, right? So therefore, now we can write that F net is going to be equal to, let's say, FA minus FB. FA minus FB. So we have to always remember, students, that when we have multiple forces acting, we have to determine the net force, right, or the resultant force by considering vectors, right, or vector addition. So that's that. Right? Huh? It doesn't matter. It doesn't really matter. Right? Remember we said the reason why we specify which one will subtract from the other one is if we have, we know the values. And we always subtract the smaller from the larger. Okay? But you could do the subtraction anyway. Right? It doesn't really matter. Okay? Alright, so that's what we see right there. Any question on that? Right? Because again, it's just coming from what we would have discussed earlier about vectors. Okay? So, and this is going to be very important to us as we look into our next formula for the net force. Okay? So, we have one expression right here for the net force, Leon. Now we're going to now establish another expression for the net force. So, we're going to say that the net force on an object is related to its acceleration by the formula all right, and this is going to be a very important formula for you. So the formula, we have F net, right? And usually we will not include this, when we start to work examples, but I'm putting it right here so that we know that it's the actual net force. Okay? The net force, F net, is equal to the mass of the object, m, multiplied by its acceleration, a. So we get F net is equal to ma. Right? So F is equal to ma. Right? So F is equal to ma. Now from this, what we see is that F net obviously would be our what? F net would be what? F net is the? F net is the resultant force, right? Or the net force. Okay? So F net is our resultant force. And this is always measured in newtons, right? So that's in newtons. M is the mass, and mass is measured in grams, kilograms, grams, kilograms, which one? Kilograms, right? So mass is measured in kilograms, so this is kg, like that. And A is our acceleration, And acceleration is measured in? No one knows? So acceleration is measured in meter per second squared. Alright? So that's our formula right there that relates the net force on an object to its acceleration. Okay? Alright? So that's the formula that relates the net force, F net, with the acceleration of the object. Okay? And just to give us some context in terms of, especially when we talk about, because we have an idea as to what a force is. It's a push or a pull, right? But in terms of acceleration now, we're going to give some context in terms of acceleration. I'm seeing some person still writing, so I'm just going to allow you to finish, and then we can talk about that. All right, so that's our formula, all right, for the net force. The net force, F net, is equal to the mass multiplied by the acceleration. Now, we know that a force is a push or a pull, right? Now, we're saying that the net force, F net, is equal to whatever the mass is multiplied by how much it accelerates. Now, when we talk about acceleration, we are essentially looking at the rate, right? And whenever students hear me say rate, I want you to always think about time. Okay? Always think about time when you hear the word rate. And we're going to be dividing by time when we hear the word rate. So once you hear rate, just think time. And you're going to divide whatever you're talking about by time. So if we're talking about the rate of something, we're going to divide whatever that is by time. Okay? So in this case, when we talk about acceleration, we're just looking at the rate at which there's a change in velocity. When we start talking about motion, we're going to go into details where this is concerned. And maybe what I will do is just define for us what is acceleration, so that we can have something meaningful going forward. Right? So I'm going to define acceleration, and I'm going to revisit explaining what we mean by acceleration. All right? So let's do that. So, acceleration. Which is written as a like that. So acceleration, this is the rate. And again, once we hear rate, we should think of time, right? And we're going to be dividing by time. So we say acceleration is the rate of change of velocity of an object. Right? So that's acceleration, the rate of change of velocity. And we can write that acceleration A is equal to, for now, you're not going to really need to use this formula, but I'm just going to ensure that I confirm to you that once we talk about rate, we're always dividing by time. So acceleration A is triangle V. What does that triangle mean? What does the triangle mean? Huh? Because I realized, yes, as I mentioned gradient, I realized that a few persons were putting this when they were working out the gradient. Right? I mean, you were on the right path, but you left out something, because when you're finding the gradient, we say that the gradient M is triangle Y over triangle X. Okay? So the triangle actually means something, right? The triangle, no, it should be like this. The triangle means a change, okay? The triangle means a change. So in this case now, we can write that this is acceleration A is equal to the change in velocity divided by what? Huh? Time, right? Because acceleration is the rate of change of velocity. So just note this down for now. When we start looking at motion, we're going to go into more details where that is concerned. All right? And we said that the SI unit is the meter per second squared. All right, so that's acceleration. That's acceleration. So again, it's the rate of change of velocity. So in other words, how much the velocity changes in a certain amount of time. That is what we mean by acceleration. So for those persons who who play Mario Kart and those Need for Speed and those kind of things, and you're selecting your car, you look at the acceleration, right? And when you are playing those games, you usually want a car that has a very high acceleration. Yes? Huh? Look at the top speed as well, right? That's the next factor. But, think about it, because let's say you have a car that has a very high top speed, but it takes long to get to that. You're going to suffer from, a slow start, right? But eventually, maybe you can pick up back in terms of, when you reach that top speed. But then again, can you maintain it, right? So usually, you want a car that has a high acceleration. So it can change its velocity from 0 to some value in a short amount of time. Okay? So that's the concept of acceleration right there. Now, we want to talk about the unit of force. Because, Michaela, we said that force is measured in Newton. Right? Now, we have a formula right here that says that the net force F is equal to the mass multiplied by the acceleration. Now, we should be comfortable, Ladin, we should be comfortable with the idea that derived quantities are formed when we multiply students or we divide base quantities, or we could do both multiplication and division. Okay? But generally speaking, whenever we form derived quantities, we're either multiplying or dividing base quantities. So, what we're going to see also then now, students, is that the unit that we use to measure our derived quantities, they're going to form by either multiplying or dividing the units of the base quantities that actually make them up. With me? So again, because we form derived quantities by multiplying or dividing base quantities, then their units are going to be formed from multiplying or dividing the units of the base quantities that actually make them up. With me? Are we clear? No? All right, so I'm going to illustrate it here so you can also see what I'm mentioning. So in this case now we have F is equal to mass times acceleration, right? So let's write this down here. So we have F is equal to mass, let's say times acceleration, right? So we say it means times now, yes? Right? F is equal to mass times acceleration. Now we say that mass is measured in kilogram, right? So we're going to get kilogram multiplied by acceleration is measured in meters per second squared. So we're going to get meters per second squared. So now, if we multiply that, what do we get? MS, go on to the slash. Right, put by the slash, right? So because we're multiplying students, we just get kilogram and we write back that. So we get kilogram meter per second squared. And this is now the derived unit for force. Okay? And if you notice, it is written in terms of base units. Because kilogram is for the base unit of mass, right? And M is the base unit of what? M by itself. M is the base unit for what? Huh? Meter, but meter is used to measure which quantity? Yes, you can go. Huh? Length, right? So this is for the base quantity, length, and S, base unit of time. Okay? So this is the SI unit of force in terms of base units. So what we see then now is that 1 Newton, students, 1 Newton, it is equivalent to what? 1 Newton is the same thing as what? Right? is equivalent to 1 kilogram meter per second squared. So what it means, students, is that if you are asked to do some calculations, and again, these three horizontal lines, they mean identical, right? Identical, right? They mean identical. So if you're given a question and you're asked to find the force and you calculate your value, you must represent it as either Newton or kilogram meter per second squared. Okay? Yes? So that's what we have right there. So let me just box this up around. Can somebody give me a time check, please? 12, so we are 15. All right. So I'm going to just use the time, and we're going to look at one example before we get out of here. But your syllabus wants you to be able to define what a Newton is. We know it is used to measure force, but we can actually define it. Right? And we're going to do that right now. So this is definition of the Newton. Of the Newton. All right, so we say that this is the force required to cause a 1 kilogram mass to be accelerated by, so the Newton is the force required to cause a 1 kilogram mass to be accelerated by what rate? Or by what acceleration? Yes? Second? No? Well, that's what we're thinking about. Again, we're trying to establish a definition for the Newton. So we're saying that it's the force required to cause a 1 kilogram mass to be accelerated by how much? How much you think? Huh? 1? 1 what? Second? 1 kilogram. No. You have the number right. You have the number right, but again we're talking about acceleration, so it must be what? Right. By 1 meter per second squared. Right? So, the Newton is defined as the force required to cause a 1 kilogram mass to be accelerated by 1 meter per second squared. Okay? So if we have a force of 1 Newton, it will cause a 1 kilogram mass to be accelerated by 1 meter per second squared. Okay? So that's the Newton. And then we're going to look at maybe a couple of examples. Yeah, we're going to look at a couple of examples in the time. Right? Make sense so far? Okay, good. So that's that. So again, we're going to look at an example. So let me just put the example here. So example. So let's say that example 1. So let's say that a box is pulled across a frictionless floor. And again, I should put in the mass. Let's say a box of mass. A box of mass. Where do you want the mass to be? Where you guys want the mass to be? Yeah? 8? 8. 8 what? 8 what? 8 kilogram, right? Because mass is measured in kilograms. So 8 kilograms across a frictionless floor. This should be one word. A frictionless floor. All right? Right? The box accelerates at, let's say, 4 meters per second squared. Calculate the net force on the box. So that's our question, right? So we have that 8 kilogram box. It was pulled across a frictionless floor. So we're talking about a very smooth floor. So we're assuming that there is no friction between the box and the table, or the floor, sorry. So if it's a frictionless floor, there's no friction between the two surfaces. Okay? So that's the assumption that we're actually making in this example. So we start out by stating our formula, which says that F net, right? F net is equal to, F net is equal to mass times the acceleration, right? So we get F net is equal to ma. Now, in our case, m is, 8 kilogram, and a is, what's a? 4, right? 4 meter per second squared. So then, we can just plug in the values. So the mass is 8 kilograms, so we have 8 kilogram times 4 meter per second squared. And what does that work out to be? Thirty-two what? Kilogram meter per second squared, right? Or we could say 32 what? Newtons, right? So 32 newtons. Whichever way, it's fine, right? You could say 32 newtons or 32 kilogram meter per second squared, because again, we say that they are identical. So you can use one in place of the other, okay? So we get 32 newtons right there for our example. So that's example 1. I'm going to put example 2 over here while you take that down. So example 2. Right? Across a floor, or let's say a table of friction, let's say it's probably 4 newtons. Okay? And we're going to sketch this out. So let's say we sketch it out. So this is our table. Let's see. So that's the table. And let's say we have our box right here. All right? Now, what we see now is that, let's say we're going to have a force. Let's say we call this force F. All right? Let's say we call it FA. All right? FA. So, we have a force acting on this box to move it across the table. But again, we say that there is a friction between the table and the box of 4 newtons. So let's say we represent that here. So we're going to use black again. So the friction, it's always moving in the direction to oppose motion. So watch me, students. Friction always act to oppose motion. So if we're pulling the box that way, the frictional force will be directed in which direction? To the opposite, right? To the left. So this is our frictional force, let's say, like so. This is Fr, right? Resistive force Fr, and let's say we call that one, it is 4, so we can put it in as 4 newtons. And let's say that this box has a mass, m. Let's say m is equal to 5 kilogram. Okay? We're going to say if the box is accelerated at, let's say, at, somebody give me a number for this. 5, okay? 5, okay. 5, I was thinking 5. Let's say, let's use 6. 6, right? 6 meters per second squared. Calculate A, the net force acting on the box. Right? So we're going to find the net force. So we start by saying that our net force, F net, is equal to what? M times A, right? Always have to write our formula, students. Right? F net is equal to M times A. Now, we're told that M is 5 kilograms, so that's 5 kilogram. And A is 6 meter per second squared. So now, this now becomes 5 kilogram times 6 meter per second squared, which works out to be what? 6 times 5 is 30, right? So this is 30 newtons. Okay? 30 newtons. Then now, just give me 5 minutes, please. Let me go through this with you. So we did part A. Part B now is going to say we need to calculate the magnitude of FA. Okay? So we're going to try to find the magnitude of FA, right, needed to produce the acceleration that is given in the question. So, to provide this acceleration of 6 meters per second squared, what is the force we need to apply? So we're going to have to go back to what we started with in terms of the net force. So we said that the net force is equal to, in this case now, by the way, we have one force going that way, one force going the opposite way. Yes? Yes? So in that case now, the net force is just going to be what? Again, opposite direction of the force, so we do what? Subtract. So the net force is going to be the difference of the two forces. So let's say we say FA minus FR. Yes. FA minus FR. Now, do we know FA? We're trying to find it, right? Do we know FR? Which is, do we know F net? Yeah, man. We know F net, right? So let's rearrange to make FA the subject. So we're going to add FR to both sides. Right? So we're adding FR to both sides. So we're going to say plus FR, and we're going to say plus FR. True? minus FR plus FR, this will actually cancel off and give you, they will cancel off each other. True? Right? So we're left with FA then. So FA then now is equal to the net force plus FR. So F net is 30. So we say 30 newtons plus FR, which is 4. So we say 4 newtons, which is, what's that now? All right? 34 newtons. That is how we do this thing. All right? So you can take this down in the meantime.